Hello, AP Chem students, and welcome to topic 9.8, Galvanic, also called Voltaic, and electrolytic cells. The learning objective for today is 9.8.a, explain the relationship between the physical components of an electrochemical cell and the overall operational principles of the cell. So, first of all, what is an electrochemical cell? So remember that during a redox reaction, electrons are exchanged between species. Now, we can harness that energy that's evolved when those electrons are moving. And we do that by separating the two half reactions and force the electrons to travel between them in a way that we can kind of collect that power, usually by having them pass through a wire. So the two half reactions are separated into what we call half cells. So you can see here that for this redox reaction that's occurring with copper and zinc, we can separate the half reactions into two half cells. So you have a copper half cell and you have a zinc half cell. In each half cell, an electrode is immersed in a solution of ions. So an electrode is a conductor submerged in a solution or molten electrolyte to carry electricity to or from the liquid. So let's talk about the electrodes a little bit more. So often the electrode is made of the solid form of whatever the metal cation is that's in the solution. So like here, you can see the solution is zinc nitrate. This is a zinc electrode. Over here, you have copper nitrate. That's a copper electrode. The exchange of electrons then occurs between the ion in solution and the solid metal electrode, like you can see here. So the solid here is losing zinc particles. They're turning into the positive zinc ions, and then your electrons are traveling up the electrode. However, sometimes you have a redox reaction that's occurring and the half reaction does not take place with the solid. It takes place, for example, with two ions, or it takes place with a gas and then ions. In that case, you would use a chemically neutral metal like platinum as the conductor, and then the exchange of electrons just happens in solution between the two ions, and then the electrons can still travel through this metal, but the metal itself is not participating in the reaction. Okay, so in this case, you can see that what's happening here is we have iron 2 that's being oxidized to iron 3. And then over here, we have kind of the situation we're used to where copper 2 is reduced to elemental copper. Okay, so let's talk about the components of the electrochemical cell individually, which is more what gets to the heart of this learning objective here. So during the redox process, electrons are exchanged between the half cells. So the electrodes in each cell, so remember that's just a piece of metal, they're connected by a wire through which electrons flow. So in this case, this reaction is occurring and they just travel through a voltmeter. And so the voltmeter allows us to determine how much voltage is being produced by this reaction. However, in order for this flow to continue, each half cell must have a net charge of 0. It's the flow of electrons that produces energy. And so to make sure that the electrons continue to flow and produce electricity, you need to have a neutral charge. So the two half cells are joined by what we call a salt bridge, which is a tube that's often in the shape of a U, so we call it a U-tube. Sometimes in the lab, we will also use like a piece of cloth or a piece of filter paper. But in those situations, if you have a tube, it's filled with an ionic or electrolyte solution. If it's a piece of cloth or a piece of paper, then we just soak it in the electrolyte solution. So this allows the ions to flow without the mixing of the two solutions. Okay, and so you can see that here. Now you would have some kind of concentration set up in your salt bridge that's high enough that you're going to create a concentration gradient so that you're not going to lose a large number of ions from the half cells. So you want your zinc, for example, to stay in this half cell. And I just saw that this is not my image, but there is a little typo here. That should be zinc 2+. So you do want the zinc to stay in this half cell. And so you would want to have a concentration that's high enough in the salt bridge that the zinc is not going to move very far into the salt bridge itself. Okay, so then the electrode at which oxidation occurs is called the anode, and the electrode at which reduction occurs is called the cathode. So let's talk a little bit more about cathodes versus anodes. So the cathode is where reduction occurs. All right, so this is this side, so that's what we're going to focus on first. So electrons are consumed, so you can see that electrons are moving down the electrode, and then the cations leave the solution and they react with the electrons that are being consumed to form more of the solid. Because of this, because cations are leaving the solution, cations from your salt bridge will migrate towards this half cell. So in this case, if the salt bridge was filled with sodium chloride, you would see that the positive sodium ions are migrating towards this half cell to replace the positive charge that's being lost when your copper 2+ ions are reacting with the electrons and forming solid copper. On the other hand, in the anode, you have oxidation occurring. So electrons are produced in this case. So you can see electrons are going to travel up the electrode and into the wire on the anode. Your cations, therefore, are going to enter solution. So your zinc solid is breaking down into the zinc 2+. So physically, the metal, the solid metal, is turning into ions that are then dissolved in the solution or dissociated into the solution. So your cations enter the solution. And then, of course, your anions would migrate from the salt bridge over to this half cell to balance the charge that's being generated by the production of your positive cations. So there's a couple tricks to remember, cathode and anode. I've got two. I like them both. The first one is car and auto, excuse me. So cathode is reduction, anode is oxidation. So that's pretty cute. You can also think about the vowels and the consonants. So cathode is reduction, anode is oxidation. Okay, so I want to show you particle diagrams because we do see these quite often on the EP exam. So let's look over here first. So if this is your starting situation before you've allowed the cell to react, you've got your zinc electrode and then you've got zinc 2+. So you have both of these in your half cell. You've got your solid electrode and you've got your solution. So then this is the anode, which means oxidation is occurring. And so if we look at the half reaction, that means that your zinc solid is going to form your zinc ion, and then 2 electrons are going to be lost. And so those electrons are going to be traveling up through the electrode and into the wire. Let me say that again. Your electrons travel through the wire. Electrons do not travel through the salt bridge. Electrons travel through the wire. Ions travel through the salt bridge to balance the charge in the half cells, which we'll look at here. So because we have a positive charge that is accumulating in my oxidation half cell, we need to have negative ions that travel in that direction to balance your charge. Over here at your cathode, we have reduction occurring. So electrons are going to travel down the wire. You can see that here into your electrode. And then those electrons react with the zinc ions that are, the copper ions that are at the surface of the metal. And then that gets reduced and forms copper metal, which then plates. And so you can see that over time, your zinc electrode is eroding because it is losing particles to the solution, whereas your copper electrode is getting bigger. It's increasing in mass because copper is being deposited. Now, again, here we are losing positive ions, and so you would have positive ions that would travel towards this half cell, and you can see that look like that. So be prepared. You might want to come back and check this slide out again and be prepared to be able to draw what's going on in these half cells and in the wire, and in the salt bridge, and then in the wire, knowing that that is where the electrons flow, because we have seen this come up on the exam before. So let's talk about spontaneity real quick. We're going to talk about this more in the next topic, but a galvanic cell produces electric current through a spontaneous process. It just happens, okay? And so we just let it go, and then we can measure, we can harness and measure the voltage. However, the production of electrical current can also be produced through a non-spontaneous process. And we talked about that when we talked about coupling reactions. We said sometimes you can plug it in and make it occur, or you can provide some kind of external energy source. We talked about sunlight being used as an external source of energy. So for electrochemical cells, we plug them in, and we can cause a non-spontaneous process to then occur. And this is called an electrolytic cell. So this type of cell is created by electrolysis, which is the process by which electrical current is used to drive an otherwise non-spontaneous process. And I think I forgot to include, yeah, I sure did. So real world examples of this include charging your battery. You plug in your cell phone to charge it at night, electroplating. So if you've got silver plated objects in your home, or if you wear white gold jewelry, white gold is just yellow gold that has been plated with rhodium. Both of those go through electrolysis. So voltaic versus electrolytic cells, the vocabulary is the same. The anode is still oxidation, the cathode is still reduction. So let me show you. So here's a picture. So you still have your anode, and that is still oxidation, and you still have your cathode where reduction is, but notice that they have flipped. Okay, and so this cadmium solution is now your cathode, and your copper is now your anode. Okay, but it's still oxidation and reduction is still the same. That doesn't change, but the flow of electrons is different. Okay, so in this case, when this happens spontaneously, the electrons are flowing from your cadmium to your copper, and that's what happens spontaneously. If we want to turn it around and make it go the other direction, we would have to plug it in and force the electrons to go in the opposite direction. So you can see then if we look at the overall reaction here, the overall reaction has flipped. Okay. Oh, and so then you can see here we have electrons that are passively going through the wire, and we can measure the voltage. Whereas on this side, we have to plug it in, and they're going in the other direction as they're being forced to do that. So what should you be able to do with this? First of all, identify the components of an electrochemical cell and the role each part plays. Determine the direction of electron flow in the cell based on if it's galvanic or if it is electrolytic. Represent an electrochemical cell with an appropriate particle diagram like we looked at on that particular slide. Label anode and cathode with a corresponding redox reaction. One thing I do want to say is galvanic and voltaic, I think I just used the word galvanic. Galvanic and voltaic cells are the same. It's just a different term for the same thing. So next topic, we're going to talk about calculating the various numerical features of cells. So I'll see you soon for that.